Hello everyone. Today we are going to solve some problems as a revision before the midterm exam. You need to solve all homeworks, okay? Understand the concept and theoretical parts we discussed in our classes, solve the problems, and uh, I urge you to solve all problems by hand. Don't read the problem answers. You have to solve it yourself and compare the results with the results you have in slides, in the textbook, or in the homework solution. Okay, and let's see some questions together to solve it today. This is example number 1.7 in the text, sorry, problem number 1.7 in the textbook. Let me. So the problem says here, two-pole synchronous machine, which is shown here in this figure. So as you can see, we have two poles. This is pole number one, this is pole number two. Okay, so let's say this is north and this is south. So we have two poles here. And with the following dimensions, so we have an air gap length of 2.5 millimeters. So this is 2.5 and this is also 2.5 millimeters. Number of turns of the coil is 500 turns and the current is 5 ampere. And here it has been mentioned that mu core equals infinity. Mu core equals infinity. This is ideal case, guys. This is ideal case. So if the permeability equals infinity, so you know reluctance equals L divide mu A. So if this is infinity, so this means reluctance will be 0. So this means we will not consider our core reluctance in the question. So you know that the relation of MMF equals N times I equals summation H times L equals summation phi times reluctance. So phi times reluctance, so this means now summation or phi core reluctance core plus phi gap reluctance gap. So this means reluctance core equals 0. Okay, and this will be the same for H. So H core times L core will be 0. Okay, so this is how we will consider the equation here. So we'll consider only the air gap in our example or our question here. So first question is draw the magnetic circuit. You know magnetic circuit, we need to find a magnetic equivalent circuit to our core. So as you can see, guys, this is the source. So this is N times I in the middle here. And when you move to this direction, you will find the first air gap. Then the flux will be distributed to the upper part of the core, lower part of the core, and return back here again and comes to another air gap and return to the same source. So we can say now this is going to be our equivalent circuit. So this is N times I. The flux is going to move in this direction. It will be distributed between the two branches of core, but again, here, reluctance core equals 0, so it's like a short circuit, okay? And it will return back again here to the other air gap and return to the supply. So this is the equivalent circuit of our or our machine. Part B, we need to find the flux density. Find the flux density, which is B. How can we get B here? So let's apply to our relation here, guys. So you know that here N times I equals, so this branch is 0. So we can say N times I equals phi times reluctance gap multiplied by 2 because we have two reluctances. So phi times 2 reluctance gap. So we can say now phi equals this term divide 2 times reluctance. So phi equals Ni times 2 divide reluctance. Substitute reluctance equals L divide mu A. So this is L divide mu A. And again, since this is reluctance of air gap, we have only mu naught because mu R for the air gap equals unity. So we can here calculate B, B equals phi divide area. So divide this relation by area. So you will find that we have two area in the numerator and denominator. So this will be omitted together. And the relation by the end will be N times I times mu naught divide 2 times L gap. Now we have 500 turns. We have 5 ampere. This is mu naught and 2 times the air length of our air gap, 2.5 millimeters. So this will be the value of our flux point 625 Tesla. Okay. So this is simply, guys, this question. Can you imagine, guys, if we didn't neglect the core? So in this case, we have to have the length of our core, the cross-section area of our core, and the permeability of our core in order to calculate the reluctance of our core. And if we have that reluctance, so we expect these reluctances to be here. So we have here reluctance core and another reluctance core here. Okay, but again here reluctance core, this is again equals 0 here because we neglected the reluctance because the permeability is assumed to be infinity for our core. Okay, so this is a first problem here. Let's solve another problem from the textbook. Problem number 8, for instance, in the sheet. So we have here, guys, electromagnetic circuits. Okay, it's like you have here a certain core with a coil, and we need to attract this bar to that coil. So let's read the problem together. So we have here electromagnet shown in figure can be used to lift a length of a steel strip. So we have a steel strip here, and we need to lift this to be attracted to our magnets. The coil has 500 turns. So this is the number of turns. So we can say here N equals 500. And carry a current of 20 ampere. So I equals 20 ampere without overheating. What the meaning of without overheating? Without overheating means this is the limit. We cannot exceed the current over 20 ampere. Otherwise, this will overheat the coil and this may burn our magnets. So this is the maximum value we should use in this case. So we shouldn't have a current higher than the 20 ampere. Then he mentioned the magnetic material has negligible reluctance at flux density up to 1.4. So it's like the previous problem now. He neglected the reluctance if the flux density up to 1.4 Tesla. So we can say here reluctance core equals 0. And the amount of B is 1.4. Then he said determine the maximum air gap. So the question is what the maximum air gap here that can be allowed for this magnet, okay? For which condition? So determine the maximum air gap for which a flux density of 1.4 Tesla can be established with a coil current of 20 ampere. So this is going to be the maximum air gap length according to the 20 ampere. And we mentioned leakage and fringing. Okay. So now, guys, we have a similar idea like the previous problem. We are going to consider only the flux and reluctance of our air gap. If we represent this circuit, guys, so this is our Ni. So we have a source here of Ni, and then this is a reluctance of core, it's neglected. Here we have one reluctance air gap. We have here another reluctance air gap and a third reluctance air gap. So we have here reluctance, we have here reluctance, and here reluctance of air gap. So this is our magnetic circuit now. So as you can see, this is Rg2, which is equal to Rg2 in right and left of our core. And in the middle here, we have Rg1, okay? What is required again? We need to calculate the length of this air gap, which will allow the current to be 20 ampere at 1.4 Tesla. So simply, guys, we can substitute now in our relations. So you know that the relation Ni equals H times summation H times L. So if you take one of the loops, so we can say Ni equals Hg times the length of the first air gap, G1, plus Hg2 times the length of air gap 2. And from the circuit here, we can say all air gap length, all lengths are the same. So we can say G1 equals G2 equals a certain length. So both of them are equal. So we can say now Ni equals Hg1 plus, sorry, Hg1 times air gap G1 plus Hg2 times G2. And we mentioned that G1 equals G2. And we can say now, since the flux density is going to be the same, so we can say Hg1 equals Hg2 equals B divided mu. And B is given 1.4 Tesla. So we can substitute in our relation now. So N equals 500, I equals 20 ampere. So this is equal now to times B divided mu naught times G. So this is, guys, can calculate the value of G required in this problem. So we got here 4.5 millimeters. So this means if you have a 4.5 millimeters, the maximum current is going to be 20 ampere. For sure, if this air gap is beyond 4.5, the amount of current will be higher in order to attract this bar of metal, which means, again, we cannot reach to this value because this is maximum value. Otherwise, you will have overheated coil, okay? So this is also another example here, guys. Let's solve a problem on synchronous machine. So for the synchronous machine, guys, you need to review the conditions of synchronization. You need to review the phasor diagrams for all cases. Okay, train yourself at home to draw the phasor diagram like what you had in the second homework. Okay, and solve all problems we had in our classes, and have a look also to the problem in the textbook, in the problem, and in the last sheet, okay, after the chapter. So this is one problem, which is problem number 18. It's more or less the same idea as the problems we solved in our class. So let's see the problem together, guys. We have a three-phase 20 kVA. So this is S rated of our machine. 208, so this is V line, V terminal line. 208 volt, 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 4 poles, so number of poles equals 4, and star connected, so the connection is Y, has a synchronous reactance, so XS equal 1.5 ohms, and the resistance of the stator winding is neglected, so assume the resistance equals 0. The machine is connected to a 3-phase 208 volt infinite bus. So the machine is going to work connected to the infinite bus. So this means the frequency and the volt are going to be constants. Now we need to calculate part A. The field current and the mechanical input power are adjusted. So the field current, IF, and the mechanical input power, which means the input torque, has been changed or adjusted so that the synchronous machine delivers 10 kilowatts at 0.8 lagging power factor. Now, is it confusing, guys? We have 10 kilowatts and we have 20 kilovolt ampere. What's the difference now? Actually, 20 kilovolt ampere, guys, is the rated value of this machine, but it doesn't mean that all of the time the machine is going to work at this power. So, for instance, if you have air condition at home, you can control the air condition temperature, and according to the temperature, it will absorb a certain power. If you have a look at the data sheet of your air condition, you will find a certain value, which is the rated power, but it doesn't mean that it will be absorbed all of the time. It depends on the operating condition. So for the time being, we are not going to use the rated value. We are going to use this value, guys, because this is the loading condition now. So we have now for part A, P equals 10 kilowatts and power factor equals 0.8, and he mentioned the type is lagging. What is needed here? Determine the excitation voltage and power angle. So we mentioned before, guys, in order to calculate EF and delta, you need either IA and power factor, S and power factor, or P and power factor. In every case, you have to have the power factor in order to calculate the current angle. Now we have P and power factor. So we can say current, or let's write the relation, P equals √3 times V line times I times power factor. This is the relation of power. So 10 kilowatt, 10 thousandths equals √3 times 208 line to line volt times the required current times power factor. Now we have one unknown only, so we can get the magnitude of current. Regarding the angle of current, we assume all of the time that the terminal volt is reference. This means the current angle is nothing but cosine inverse power factor. So here, this is textbook solution. He mentioned that theta equals cosine inverse power factor. So this is cosine inverse 0.8. Okay, but take care, the power factor is lagging, which means by the end you have to say IA equals the magnitude of current 34.7 ampere at minus 36.87 degree. So this is the current vector. Now we need to calculate EF and delta. We can substitute now in our relation. So we neglected the resistance in this problem, so we can say V terminal plus GIAXS. If you have a look at the nameplate data here, he mentioned 208 volt, but we mentioned that this volt is line to line. And this equation is for a single line diagram. So this is single line diagram. So we have to use phase values. So in this case, guys, we have to mention here V phase. So V phase is V line divided root 3 because we assumed it's Y connection. So 208 divided root 3 equals 120 volt. So this is the VT he used here in this problem. Plus current times or at angle minus 36, again minus sine Y because this is lagging power factor. And this is JXS or XS at angle 90 degrees. If you calculate this value, guys, you will find the phase volt is 156.8 and the angle is plus 15.4. Remember that plus sign for power angle means this is in generator mode. Okay. Okay, so we finished now the first part of this question. The second part here, guys, we need to, I said the mechanical input power is kept constant. So once you hear, guys, the power is kept constant, so remember the relation of constant power. So what are the relation of constant power? EF sine delta is constant, or IA power factor is constant. So you can say EF1 sine delta 1 equals EF2 sine delta 2, or IA1 power factor 1 equals IA2 power factor 2. And 1 and 2 are the two operating conditions, like what we have here. Part A is an operating condition and part B is another operating condition. So he mentioned again the mechanical power is kept constant, but the field current is adjusted. So he adjusted the field current for a certain reason. What is that reason? He mentioned adjusted to make the power factor unity. So the second case now, we knew that power factor 2 equals 1. And power factor 1 is given 0.8. What is needed here? Determine the percent change in the field current with respect to the value in part A. So we have a certain field current in part A. What is the change in the field current in the second part? So for the field current, guys, we have no relations for field current, but we can compare field current with excitation because change or percent change in excitation volt will be the same as the percent change in the field current. So this means, guys, we need to get the percent change in the excitation volt, which will be the same as the change in the field current. So now, simply we have the second power factor, we have the first power factor, so we can get the second current. So the solution here is, we can say that second current equals the same amount of power, since the power is constant, divide root 3, 208. So this is the amount of current. So he used, guys, here the power and the same volt, and he substitutes the power factor as unity. Let me write the relation, guys, so the textbook solution is not clear enough. So we mentioned that, let's say IA1 power factor 1 equals IA2 power factor 2. So we have IA1, which was given, calculated 34.7. So we have 34.7 times power factor 1 is 0.8. So this is equals IA2 times power factor 2, which is unity. So from here, we can get IA2. Another way, which is the solution here, we can say IA in the second case equals the same power, because it's constant, divide root 3 times V line times power factor 2. So this is going to be 10 kilowatt divide root 3 times 208 times unity. So this is going to provide us our second current. And after getting this current, guys, we can calculate the value of excitation volt. So since the power factor is unity, so this means the angle current, the current angle is 0. So we can say now EF equals VT at angle 0 plus this is IA2 here, and this is 0 angle because it's unity power factor times JXS. So we got now the second value of the excitation volt. Now, compare the excitation volt 127 with the 156. So this is going to provide the same ratio of IF. So we can say IF of the second case B divide IF of the second case A equals EF second case. So this is EF2 and this is EF1. And multiply times 100 in order to get it in percent. So you will find that the ratio is 80%. So this means, guys, we reduced the excitation to 80%. Again, so we reduced excitation to 80.96%. So this reduction in excitation, expect to have increase or decrease in power angle, guys. What do you think? It has to be increased. So if the flux is reduced, the power angle will increase. Okay, so the first power angle was 15. The second power angle here is 19. So this is expected here in this case since we reduced the excitation. Okay, so please, guys, review all problems we solved in our class. Review the phasor diagram, how to draw the phasor diagram. Review the meaning of excitation. Review the construction of the machine, the different shape. Compare between salient pole and cylindrical pole. Okay, and you will find some of these questions in the midterm exam. Thank you so much, guys. Please see the video. I will share with you the video and the material we solved it now. And if you have any question, send me on my email and I will respond as soon as possible. Thank you so much and have a nice day.